Welcome to the session on overview of I/O devices. A computer is an electronic machine that accepts data from the user, processes the data by performing calculations and operations on it, and generates the desired output results. A computer system consists of both hardware and information stored on hardware. Information stored on computer hardware is often called software. The hardware components of a computer system are the electronic and mechanical parts. The software components of a computer system are the data and the computer programs. The major hardware components of a computer system are processor, main memory, secondary memory, input devices and output devices. Input and output devices. An input device sends information to a computer system for processing, and an output device reproduces or displays the results of that processing. Computer input is called data, and the output obtained after processing it based on user's instructions is called information. Raw facts and figures which can be processed using arithmetic and logical operations to obtain information are called data. Some input devices are graphic tablets, cameras, video capture hardwares, trackballs, barcode readers, digital camera, gamepad, joystick, keyboard, microphone, MIDI keyboard, mouse, scanner, webcam, touchpads, pen inputs, microphone, electronic whiteboard, OMR, OCR, punch card reader, MICR and magnetic tape drive. Output, the results produced by the central processing unit, is a computer's whole reason for being. Output is usable information, that is raw input data that has been processed by the computer into information. The most common forms of outputs are words, numbers and graphics. Word output, for example, may be the letters and memos prepared by office people using word processing software. Other workers may be more interested in numbers such as those found in formulas, schedules and budgets. In many cases, numbers can be understood more easily when output in the form of charts and graphics. Some output devices are monitors, printers, plotters, projectors, LCD projection panels, computer output microfilm, speakers, headphones, visual display unit, film recorder and microfiche. Connection ports. Port is a connecting socket outside the system into which different types of cables are plugged. It is a specific place from which other devices can be physically connected. I/O ports are the interfaces through which computers communicate with external devices such as printers, modems, joysticks and terminals. There are many types of ports used in computer system. Some of them are given as follows. Parallel port. Various peripherals can be connected through parallel port, which is a parallel communication physical interface. A parallel port transmits 8 bits of a byte of data in parallel. It is used for transmitting fast data over short distances. It is used to connect a printer to a computer. Since a parallel port transmits an entire byte at a time, it operates I/O devices at a relatively high speed. A parallel port is primarily used to connect printers to a computer and hence it is often called a printer port. Serial port. Serial port transmits 1 bit of a byte, one at a time, as a single stream of bits. It is meant for transmitting slow data over long distances. Communication over a phone is an example of serial communication. It is a serial communication physical interface which transmits 1 bit at a time. Dial-up modems and serial mice use serial ports. Universal Serial Bus or USB. A USB port can connect up to 127 peripheral devices such as a digital camera, digital speakers, scanners, etc. It permits plug and play, which means that configuration of expansion cards and peripheral devices as and when they are installed. Small Computer System Interface or SCSI port. SCSI, that is Small Computer System Interface port, allows data to be transmitted in a daisy chain up to 7 devices at a speed higher 32 bits at a time than those possible with serial and parallel ports. It is a fast data transmitting device and is used to connect HDD, CD-ROM drivers and scanners with the computer system. I/O device types. An I/O system is required to take an input request from some application and send it to the physical device, then take whatever response comes back from the device and send it to the application. I/O device can be divided into two categories. Block devices. A block device is one with which the driver software communicates by sending entire blocks of data. For example, hard disk, USB cameras, disk on key, etc. Character devices. A character device is one with which the driver communicates by sending and receiving single characters, bytes, octets, etc. For example, serial ports, parallel ports, sound cards, etc. External devices. I/O operations are accomplished through external devices that provide a means of exchanging data between external environment and computer. An external device attaches to the computer by a link to an I/O module. An external device linked to an I/O module is called peripheral device or peripheral. External device can be categorized as human readable and machine readable. Human readable means suitable for communicating with computer user. For example, video display terminals and printers. Machine readables are suitable for communicating with equipment. For example, sensor, actuators used in robotics application. Communication suitable for communicating with remote devices. They may be human readable device such as terminal and machine readable device such as another computer. Properties of devices. The number and types of input devices and output devices available in the market today can be completely confusing. Fortunately, there are a number of organizing properties and principles which can help to make sense of the design space and performance issues. Physical properties sensed. Traditional pointing devices typically sense position, motion or force. A tablet senses position, a mouse measures motion, that is change in position, and an isometric joystick senses force. An isometric joystick is a self-centric force sensing joystick such as the IBM TrackPoint, eraser head found on many laptops. For a rotary device, the corresponding properties are angles, change in angle and torque. Position sensing devices are also known as absolute input devices, whereas motion sensing devices are relative input devices. An absolute device can fully support relative motion since it can calculate changes to position, but a relative device cannot fully support absolute positioning and in fact can only emulate position at all by introducing a cursor on the screen. Note that it is difficult to move the mouse cursor to a particular area of the screen other than the edges without looking at the screen. But with a tablet, one can easily point to a region with the stylus using the kinesthetic sense informally known as muscle memory. Transfer function. A device in combination with the host operating system typically modifies its signals using a mathematical transformation that scales the data to provide smooth, efficient and intuitive operation. An appropriate mapping is a transfer function that matches the physical properties sensed by the input device. Appropriate mappings include force to velocity, position to position and velocity to velocity functions. For example, an isometric joystick senses force. A non-linear rate mapping transforms this into a velocity of cursor movement. Ideally, the device should also be self-centric when using a rate mapping with a spring returned to the zero input value, so that the user can stop quickly by releasing the device. A common inappropriate mapping is calculating the speed of scrolling based on the position of the mouse cursor, such as extending a selected region by dragging the mouse close to the edge of the screen. The user has no feedback of when to or what extent scrolling will accelerate, and the resulting interaction can be hard to learn how to use and difficult to control. A simple multiplicative transfer function is known as the device gain, which can also be described as a control to display, that is CD ratio. The ratio between the movement of the input device and the corresponding movement of the object it controls. Number of dimensions. Devices can measure one or more linear and angular dimensions. For example, a mouse measures 2 linear dimensions, a knob measures 1 angular dimension, and a 6 degree of freedom, 6D of magnetic trackers measure 3 linear dimensions and 3 angular dimensions. If the number of dimensions required by the user's interaction task does not match the number of dimensions provided by the input device, special handling mechanisms are to be introduced. This may include extra buttons, graphical widgets, mode switching, etc. Pointing speed and accuracy. The standard way to characterize pointing device performance employs the Fitts-Low paradigm. Fitts-Low relates the movement time to a point at a target, the amplitude of the movement, that is the distance to the target, and the width of the target, that is the precision requirement of the pointing movement. The movement time is proportional to the logarithm of the distance divided by the target width, with constant terms that vary from one device to another. Input device states. To select a single point or region with an input device, users need a way to signal when they are selecting something versus when they are just moving over something to reach a desired target. The need for this fundamental signal of intention is often forgotten by researchers eager to explore new interaction modalities such as the empty-handed pointing, example using camera tracking or non-contacting proximity sensing of hand position. The three-state model of input generalizes the states censored by input devices as tracking, which causes the cursor to move, drag, which allows selection of objects by clicking as well as moving objects by clicking and dragging them, and out of range, which occurs when the device moves out of its physical tracking range. Example, mouse is lifted from the desk or a stylus is removed from a tablet. Most pointing devices sense only two of these three states. For example, a mouse senses tracking and dragging, but a touchpad senses tracking and the out of range state. Hence, to fully simulate the functionality offered by mice, touchpads need special procedures such as tapping to click, which are prone to inadvertent activation. Example, touching the pad by accident causes a click. Direct versus indirect control. A mouse is an indirect input device. One must move the mouse to point to a spot on the screen. A touch screen is a direct input device, that is the display surface is also the input surface. Direct devices raise several unique issues. Designers must consider the possibility of parallax error resulting from a gap between the input and display surfaces, reduced transmissivity of the screen introduced by a sensing layer, or occlusion of the display by the user's hands. Another issue is that touchscreen can support a cursor tracking state or a dragging state, but not both. Typically, touchscreens move directly from the out of range state to the dragging state when the user touches the screen with no intermediate cursor feedback. Device acquisition time. The average time to pick up or put down an input device is known as acquisition time or sometimes homing time. It is often assumed to be a significant factor for user performance. However, one exception is stylus or pen-based input devices. Pens are generally comparable to mice in general pointing performance. Modeling of repetitive tasks. The keystroke level model (KLM) is commonly used to model expert user performance in repetitive tasks such as text editing. The KLM includes standard operators that represent average times required for pointing with an input device. Pressing a button poses for decision making and device acquisition time, but the model does not account for errors or non-expert behavior such as problem solving. Hardware criteria. Various other characteristics can distinguish input devices but are perhaps less important in distinguishing the fundamental types of interaction techniques that can be supported. Engineering parameters of a device performance such as sampling rate, resolution, accuracy and linearity can all influence performance. Latency is the end-to-end delay between the user's physical movement, sensing this and providing the ultimate system feedback to the user. Latency can be a devious problem as it is impossible to completely eliminate from system performance. Latency of more than 75 to 100 milliseconds significantly impairs user performance for many interactive tasks. Device modes of I/O data transfer. Data transfer between the central unit and I/O devices can be handled in generally three types of modes which are given below: programmed I/O, interrupt initiated I/O and direct memory access. Programmed I/O instructions. Programmed I/O instructions are the result of I/O instructions written in computer program. Each data item transfer is initiated by the instruction in the program. Usually, the program controls data transfer to and from CPU and peripheral. Transferring data under programmed I/O requires constant monitoring of the peripherals by the CPU. Interrupted initiated I/O. In the programmed I/O method, the CPU stays in the program loop until the I/O unit indicates that it is ready for data transfer. This is a time consuming process because it keeps the processor busy needlessly. This problem can be overcome by using interrupt initiated I/O. In this, when the interface determines that the peripheral is ready for data transfer, it generates an interrupt. After receiving the interrupt signal, the CPU stops the task which is processing and serves the I/O transfer and return back to its previous processing task. Direct memory access. Removing the CPU from the path and letting the peripheral device manage the memory buses directly would improve the speed of transfer. This technique is known as DMA. In this, the interface transfers data to and from the memory through memory bus. A DMA controller manages to transfer data between peripherals and memory unit. Many hardware systems use DMA such as disk drives controllers, graphic cards, network cards and sound cards, etc. It is also used for intra-chip data transfer in multi-core processors. In DMA, CPU would initiate the transfer, do other operations while the transfer is in progress and receive an interrupt from the DMA controller when the transfer has been completed. User interface transactions. Early efforts in human-computer interaction sought to identify elemental tasks that appear repeatedly in human-computer dialogues. User interface transactions are composed of the following elemental tasks: selection, choosing objects from a set of alternatives; position, specifying a position within a range. This includes picking a screen coordinate with a pointing device; orient, specifying an angle or three-dimensional orientation; path, specifying a series of positions and or orientation over time; quantify, specifying an exact numeric value; text, entry of symbolic data. I/O module. I/O module is intermediate between I/O devices and CPU. System buses are connected to the one end of I/O module and other end is connected to the number of I/O devices. It is used to exchange information between I/O devices and CPU. I/O devices cannot be directly connected to the system buses. They are connected to the system buses through module. There are several reasons for not connecting I/O devices directly to the system buses, and they are as follow. Variety of I/O devices are available with different operation method. It was not possible to develop operation logic for each I/O devices in the CPU list. The I/O devices are much slower than the CPU. Hence, it is not possible to match the high speed of CPU with the speed of I/O devices. As I/O devices are made with different operation methods, some of them uses different data formats. It was impractical to integrate each data format in the CPU. Thus, I/O module is used to match speed, operation method and data format between CPU and I/O devices. Functions of I/O module. The major functions of modules are categorized as follows. Control and timing. In some of the I/O operation, few resources shared such as CPU and memory because CPU communicates with more than one device at a time. Control and timing function synchronizes data flow between I/O devices and internal resources such as memory and CPU. Processor communication. I/O module communicates with the CPU and I/O devices. It performs following steps. Status inquiry of I/O device from I/O module. I/O module accepts data from the I/O device and transfers it to the CPU. Device communication. In addition, I/O module communicates with I/O devices. Feature of I/O module. Data buffering. As I/O devices are much slower than CPU and memory, in order to maintain speed of data flow between I/O devices and internal resources, I/O module buffers data. Devices can access buffered data anytime without holding system bus. Error detection. It is a built-in feature of I/O module that detects electrical and mechanical errors. I/O drivers and controllers. All peripherals require driver software which enables the OS to command the hardware. When a peripheral device is added that is new to the computer, a controller card is plugged in and a driver is installed. Every peripheral device such as keyboard, modem, monitor, etc. requires a control unit that interfaces with the computer's processor, that is the CPU. These circuits are either built into the chips on the motherboard or are contained on plug-in cards. The input or output controller is a device that interfaces between an input or output device and the hardware device. The input-output controller on a computer is commonly located on the motherboard. However, an I/O controller can also be an internal add-on that can either be used as replacement or allow for additional input or output devices for the computer. The device controller works like an interface between a device and a device driver. I/O units such as keyboard, mouse, printer, etc. typically consist of a mechanical component and an electric component, where electric component is called the device controller. There is always a device controller and a device driver for each device to communicate with the operating system. A device controller may be able to handle multiple devices. As an interface, its main task is to convert serial bit stream to block of bytes, perform error correction as necessary. Now let us summarize the session. Input-output device is any hardware used by a human operator or other systems to communicate with a computer. As the name indicates, input-output devices are capable of sending data or output to a computer and receiving data from a computer input. The way system manages different types of inputs and outputs depend on the I/O system. Here, an overview of the I/O devices and the system is given to get an idea about the different types of input devices, the connection ports used to connect different peripherals, the mode of data transmission, etc. The session ends with an introduction to I/O drivers and I/O monitors. Hope you enjoy this session. See you next time. Bye.